In the signaling game of graph 24.9, beliefs didn't matter very much. This was because the receiver knew exactly what his best response would be if he observed the signal left, and what his best response would be if he observed the signal right. And that best response had nothing to do with what he believed the sender to be, whether he believed the sender to be a type 1 sender or a type 2 sender. We'll now change that game slightly and see how beliefs can play an important role in sequential incomplete information signaling games. We begin by simply replicating the game tree from graph 24.9. Notice that the highlighted actions by the receiver are the same on the left and they are the same on the right. In other words, the receiver doesn't care who sent the signal. If he receives a signal left, he knows to go up, and if he receives a signal right, he knows to go down. Now suppose that we change the magenta payoff of 0 in the upper right corner to a 10. In other words, if a sender of type 1 sends a signal right, and the receiver responds by playing up, we're changing the receiver's payoff from 0 to 10. Now the receiver begins to care about who it is that sent the signal right. If it's a type 1 sender, then it becomes optimal for the receiver to play up instead of down, because that gives a payoff of 10 rather than 5. If, on the other hand, a type 2 sender sent the signal right, it continues to be optimal for the receiver to play down and get 5 rather than 0. Suppose then that the receiver, after observing the sender going right, believes the sender to be a type 1 with probability delta and a type 2 with probability 1 minus delta. If he then goes up, he gets a payoff of 10 with probability delta and a payoff of 0 with probability 1 minus delta for an expected payoff of 10 delta. By going down, on the other hand, he gets a payoff of 5 regardless of what type the sender was. 10 delta is larger than 5 when delta is greater than 0.5. So if the receiver believes the sender to be a type 1 sender with probability greater than half after observing the signal right, the receiver will go up rather than go down. On the left side of the game tree, beliefs continue to not matter, because the receiver knows that as soon as he receives a signal left, his best response is to go up, regardless of what type the sender was. We indicate here with gamma the receiver's belief that the sender is a type 1 after sending the signal left. Gamma then can take any value from 0 to 1, and the receiver's best response will be to go up. We then have two types of perfect Bayesian-Nash equilibria to this game. The first is a pooling equilibrium, where both sender types send the same signal, in particular the signal left. This can only be part of a perfect Bayesian-Nash equilibrium, however, if a sender of type 1 knows that the receiver will go down if he observes the signal right. And we've just concluded that a receiver will go down if he observes right only if delta is less than half. In other words, only if he believes, after observing the signal right, that the sender is a type 1 with probability less than 1/2. The pooling equilibrium must then specify not only a plan of action for each information node that each player might arrive at, but also a set of beliefs that makes the behavior equilibrium behavior. The strategies in this pooling equilibrium would be left-left for the sender. In other words, the sender plans to go left regardless of what type she's assigned. The strategy for the receiver is to go up if he observes left and down if he observes right. The equilibrium beliefs gamma can take any form. In other words, gamma can lie anywhere from 0 to 1. But the belief delta must lie below 1/2 in order for this pooling equilibrium to be a perfect Bayesian-Nash equilibrium. Notice that in this equilibrium, the action right is never actually played by the sender. Nevertheless, the beliefs that the receiver holds in the event that right were played matters in terms of supporting this as-equilibrium behavior. If delta were greater than 0.5, subgame perfection would require that the receiver play up after observing the signal right. But that then would imply that a type 1 sender would be better off by sending the signal right, and the pooling behavior of both sender types sending the signal left would no longer be in equilibrium. The second type of perfect Bayesian-Nash equilibrium in this game is known as a separating equilibrium, an equilibrium where the two different sender types send different signals, and as a result, the receiver knows exactly what type he's facing when he's receiving a signal. The separating equilibrium strategies for the sender would be right, left. In other words, a plan to send the signal right if type 1 is assigned to the sender, and a plan to send the signal left if a type 2 is assigned to the sender. The only internally consistent beliefs for the receiver to hold are then delta equal to 1 and gamma equal to 0. In other words, if the sender plays the strategy right-left, then when the receiver observes right, he knows he's encountering a sender of type 1, whereas if the receiver sees a signal left, he knows he's encountering a sender of type 2. Given these beliefs, it is then the best response for the receiver to go up after observing right and to go up after observing left. And given those strategies, neither sender type could do better by deviating from the strategy right-left. The separating equilibrium is then right-left for the sender, up-up for the receiver, with the equilibrium beliefs of delta equal to 1 and gamma equal to 0.